Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at the derivative of the tangent function as well as the cotangent function. In the previous two videos we looked at finding the derivative of the sine function and the cosine function and doing a number of examples, combining that with our other rules such as power rule, quotient rule, and product rule. So if u is a function of x and we're asked to differentiate sine of u with respect to x, the derivative would be cos of u times du dx, and that comes from our chain rule. Similarly, if we are asked to find the derivative of cos of u with respect to x, its derivative would be negative sine of u du dx. So in this video, we could find the derivative of tangent of u and cotangent of u by writing both those functions in terms of sine and cos, because our basic identities tell us that tan of u is equivalent to sine of u divided by cos of u. And similarly, cotangent can be expressed as the ratio of cos of u over sine of u. Because we know how to differentiate quotients and we know how to differentiate sine functions and cos functions, I can differentiate this now. So this derivative would be equal to the denominator, I'm using the quotient rule, so the denominator times the derivative of the numerator. The derivative of the numerator is cos of u du dx minus the numerator times the derivative of the denominator, which is derivative of cos of u is negative sine of u du dx, over the denominator squared. I'm just simply plugging into my quotient rule. Then when I simplify this, I would get cos squared u times du dx. That becomes plus sine squared u du dx, and my denominator stays the same. Then what I could do is factor out a du dx in the numerator, and my Pythagorean theorem allows me to simplify cos squared u plus sine squared u is simply 1. So this derivative would be equal to 1 over cos squared u du dx. And another one of my basic identities allows me to write 1 over cos squared u as secant squared u. Therefore, I can find the derivative of tan u by using this formula. We could do the same thing in order to find the formula for the derivative of cotangent. We express cotangent u as cos u over sine u. We differentiate using our quotient rule. It would be a very similar process, and we can obtain the derivative in that way. If I were to do that process, I would end up with a derivative of negative cosecant squared u du dx. And it's a good exercise to try on your own. Write it in terms of cos of u over sine of u. Use your quotient rule, differentiate, and see once you simplify if you can get this answer. So these are the two rules or formulas that we're going to work with in this video. So let's just use these formulas in doing some derivative examples. In our first example, we have y equals 5 times the tangent of 4x minus 1. So in this case, our u is 4x minus 1. So we take the derivative of this and plug into our formula. The derivative of tangent of u is secant squared of u, and then we multiply by du dx, so the derivative of 4x minus 1 is 4. Let's bring that 4 and multiply it with the 5 and put it out front here, so that we get the derivative of this function will be 20 times the secant squared of 4x minus 1. Let's try some more. I want to do these next two examples on the same board because they're similar in that they both have a cotangent function, they both have a square root function or a power function, and they both have a polynomial function. but the way in which we differentiate is going to be different because the outermost function is different in this one compared to this one. So for example, with this question, our outermost function is the cotangent function. And then when we go inside of that, we have the power function. And then when we go inside of that, we have the polynomial. Before I start, I want to write this as x squared minus 2 to the 1/2. And then I differentiate. So the derivative will be, the derivative of the cotangent function will be negative cosecant squared of x squared minus 2 to the 1/2. So I've got the derivative of cotangent. Now I go inside the cotangent function and I've got a power. So the derivative of that will be 1/2 times x squared minus 2 to the 1/2 minus 1. Then I go inside the power and I have x squared minus 2. The derivative of that is 2x. Then when we clean it up, we can combine 1/2, 2x, and that negative sign to give me negative x. This has a negative exponent, so I'm going to put it in the denominator. And this I'm just going to write as cosecant squared. You can leave it to the power of 1/2. Or you could replace it with square root, since that's what the original question looked like. And then in the denominator, I'm going to have x squared minus 2 to the power of 1/2. Again, we could write that as square root. Just be careful that you do not cancel. This is not a factor. It's the cosecant of this. It's not cosecant times that. So just be very careful. You can only cancel common factors, which means that they're multiplied. So that would be our final result. In this question, before I start, I'm going to write that as cotangent of x squared minus 2, the whole thing to the power of 1/2. And when I differentiate that, the outer function is a power, so I have to start there. So my derivative will be 1/2 times this function to the power of 1/2 minus 1. Now I go inside the power function and then I have a cotangent function. So I multiply by the derivative of cotangent, which is negative cosecant squared of x squared minus 2. And then I go inside the cotangent function and I have x squared minus 2. The derivative of that is 2x. When we clean this up, I've got the 1/2 times negative 1 times 2x will give me negative x. That's going to go in the denominator. And this cosecant squared of x squared minus 2 stays in the numerator. And this can be written as square root or to the power of positive 1/2. Again, because it was written as square root there, you might want to write it as square root instead of to the power of 1/2. But I just wanted to point out the difference and understanding how you start the derivative and move in. Let's take a look at a couple more examples. We have a product. We have 4t squared multiplied to the tangent of 6t. So, here's our product rule that we're going to have to plug into. Identify your u and your v. So u would be equal to 4t squared. And u prime will therefore be 8t. V is tangent of 6t. So the derivative of that would be secant squared of 6t multiplied to the derivative of 6t, which is 6. So I'll pull that in front. Now we just plug into our product rule. So our derivative will equal u, which is 4t squared, times v prime, which is 6, times secant squared of 6t, plus v, which is tangent of 6t, times u prime, which is 8t. I just clean this up a little bit. 4 times 6, so I've got 24t squared, secant squared 6t, plus 8t tan of 6t. And there's really no simplification. I mean, some people might want to factor in 8t out, but really it's not going to be any simpler if we do. So I would leave it like this. Let's do one more example, and in this next example I want to evaluate the derivative at a specific value of our independent variable. In our last example we have a quotient, and we're asked to evaluate the derivative at x equals 0.5. So we're going to use the quotient rule. I've already outlined what u is, the numerator, and the derivative of that, v, and the denominator. Now I'm going to plug these values into the quotient rule. So the derivative in general will be 4x v times u prime, which is -2 times secant squared of 2x, minus u, which is 3 minus tangent of 2x, times v prime, which is 4, all over the denominator squared. So I'm going to get -8x times secant squared of 2x minus, I'm going to distribute that 4, so that's -12. Negative times a negative is positive, 4 times the tangent of 2x over 16x squared. Now what I want to do is evaluate that when x is equal to 0.5. And I'm going to write that as secant of 2 times 0.5. And I'm going to put the square outside because I want to find the secant first and then I want to square the function. So we'll get -4. And the other thing I'm going to do is I'm going to write secant. So it's a secant of 1, but I'm going to write that as 1 over cos of 1. .5 squared is 0.25 times 16 is 4. When you evaluate this, you have to make sure your calculator is in radian mode. It says, you know, tangent of 1, cos of 1. There's no degree symbol there. So when you're working with angles and no unit of measure is given, you assume radians. So I enter this into my calculator, making sure that my calculator is in radian mode. And when I calculate this, I get a value of -4.87. So sometimes you're just asked to find the derivative in general form, and sometimes you're asked to evaluate it at a specific value. So I just wanted to do this because we are working with trig functions, and I wanted to remind you that you need your calculator to be in radian mode to do these questions. We're going to move on in the next video to the derivative of secant and cosecant. So practice some tangent and cotangent questions first, and when you're ready, I'll see you in the next video. Take care.